Next talk will be given by Tamar Zelovich. Now, so the Nano Center distributes every year, as you might know, several special fellowships for particularly excellent students and postdocs, and Tamar was one of them. So Tamar will tell us. She's a student of Oded Hod from chemistry, and she will tell us about state representation approach for atomistic time-dependent transport calculation in molecular junctions.
So hi, thank you. I'm Tami, and I'm a PhD student in Oded Hod's group from Tel Aviv University and in Lior Kronis group from the Weizmann Institute. And the title of my talk today, I'll say the state representation approach for atomistic time-dependent transport calculation in molecular junctions. Hopefully, you will all understand the title of my talk until the end of it. My work is related to the field of molecular electronics, and in particularly to electron dynamics in open quantum systems. Let's start with molecular electronics. In those systems, we have three main parts. We have the source, the drain, and the molecule that's in between. Now, the source and the drain are two reservoirs, which are held at two different chemical potentials. And the chemical potential defines our Fermi function. So as a result, we have a higher occupancy in the source and a lower occupancy in the drain, so electrons will want to move from one side of the system to the other, the same as water flows from a high place to a lower one. Now, in those systems, we have two main parameters that helps us control the system. The first one is this potential differences gap between the source and the drain. And the second one is which levels and how many levels are free in the molecule in this potential differences gap. Now, when working on the molecular scale, as we do in molecular junctions, the size of the system is of the order of several nanometers, meaning it is of the order of the wavelength of the electron. So as a result, we now have quantum conductance and quantum effects in the system, and the electronic structure of the molecule starts to play a role. So as a result, we now have much higher sensitivity to the environment, to temperature, to external molecules, to laser light. So we can have much better detectors and better sensors, and we can actually control the system using laser pulses. So for all of those reasons, it is important to explore and to understand the electron dynamics in those single molecule junctions. Now, when I'm saying open system, what do I mean? So if I'm looking at the whole system, it does not exchange energy and electrons with the rest of the universe. So this is a closed system. But if I'm looking on the molecule, then it does exchange energy and electrons with other parts of the system, meaning we are injecting electrons from the source to the molecule and then absorb the electrons from the molecule to the drain. So when I'm saying open system, I'm actually referring only to the molecule, which is the active region. So when we want to build a theoretical model for those kind of systems, our main challenge will be to describe the time-dependent dynamics of a non-equilibrium behavior in an open quantum system. Meaning we want to be able to describe the different occupancies on each of the leads. We want to characterize the current dynamics and to describe the injection and absorption of electrons to the system. And we want to be able to do it for long time scales so we can achieve a true steady state. Now, when choosing a theoretical model, there are two different point of views which are usually discussed separately. There's the site representation and the state representation. The site representation is the real space picture, the atomistic picture. And the main advantage when working with a site representation is that now we can control the junction geometry, the lead dimensionality, and the lead shape. The state representation, on the other hand, is the energy representation. Here we are looking on the different states of the different parts of the system and on the couplings between them. And the main advantage when working with a state representation is that now we can use the Fermi-Dirac distribution and have a specific bias voltage and lead electronic temperature. So in order to enjoy the advantages of both representations, we are suggesting our model which is based on a unique transformation from site to state representation. And again, transforming between the two representations enables us treating atomistic junction models with the appropriate boundary condition. And when I'm saying boundary condition, I mean a specific bias voltage and lead electronic temperature. So how can we do that? How can we transform from the site to the state representation? Our starting point is the site representation, and we are building the Hamiltonian for this atomistic picture. Looking on the Hamiltonian, we can see we have the diagonal elements, HL, HM, and HR, which represents the different parts. HL for the left lead, HM for the molecule, and HR for the right lead. And we have the off-diagonal elements, the V's, which represents the couplings between the different parts. Now, at the next stage, we are diagonalizing each part of the system separately. By diagonalizing HL, we get the states for the left lead. By diagonalizing HM, we get the states for the molecule. And by diagonalizing HR, we get the states for the right lead. Now, using UL, UM, and UR, we have already found, we can now define a global transformation matrix U. And using this global transformation matrix U, we can now transform from the Hamiltonian of the site representation to a full Hamiltonian in the state representation. And looking on the Hamiltonian in the state representation, we can see that in addition to HL, HM, and HR we have already found, we are now adding the V terms, which represents the couplings between the different states. And again, after transforming to the state representation, we can use the Fermi-Dirac distribution and have a specific bias voltage and lead electronic temperature. And as a result, we have different occupancies on each side of the leads. So electrons will want to move from one side of the system to the other. Again, the same as water flows from a high place to a lower one. Up until now, comparing our site to state representation to the site and to the state representations, we can see that in the site representation, we can treat atomistic junction models, but we can't have a specific bias voltage and lead electronic temperature. In the state representation, we can't treat atomistic junction models, but we can have a specific bias voltage and lead electronic temperature. And using our site-to-state representation, we can treat atomistic junction model, we can have a specific bias voltage and lead electronic temperature. So what remains now is to open the system and to have a true steady state, but we still want to obey the Pauli principle. So in order to open the system and to have a true steady state, we are using the driven Liouville-Van Neumann equation for the density matrix. Our goal is to use a finite system, as we can see here, a finite system, in order to model the behavior of an open quantum system. And again, in order to do so, we're using the driven Liouville-Van Neumann equation for the density matrix. This equation has three parts. The first one is the standard Liouville equation. This is good for closed system only, and this is equivalent to propagating the wave function using the time-dependent Schrödinger equation. Now, in order to understand this part of the equation, let's assume we have some initial polarized state. So as a result, we have a negative charge on the left side and a positive charge on the right side. Now we are propagating the density matrix using this Liouville equation. And what we are actually looking at is the discharge of two large but finite electrodes, which is actually the behavior of a capacitor. So as a result, we now have the negative charge on the right side and the positive charge on the left side. But this is a closed system, meaning as the wave packet reaches the edges of the lead models, we will see reflections of the wave packet back to the molecule. And as a result, we have now again the negative charge on the left side and the positive charge on the right side. So the problem here is how can we overcome those reflections and to maintain in our initial state? And the solution is to describe the injection and absorption of electrons, and we are doing it by adding a driving term to the equation. So the driving term has two parts. The first one is the density matrix at the left and right lead models in our initial state. This is with a plus sign, therefore it represents the electron injection to the system. The second part is with a minus sign, therefore it represents the electron absorption from the system, and we can see that we are dumping the bad blocks and the bad molecule coherences blocks as well. So using this equation, we are now able to describe the injection and absorption of electrons by forcing the density matrix at the left and right lead models back towards our initial density. And we can see now that we can maintain our initial state in the site representation and in the state representation. And in the state representation, the initial charge imbalance represents the Fermi-Dirac distribution at the left and right lead models with the appropriate chemical potential. So some results. As a first model, we chose a one-dimensional chain of atoms in a tight binding model, and we are measuring the current in the middle of the molecule. Here we can see the current as a function of time. The black curve represents the result using the Liouville equation. So you can see we have a quasi-steady state which persists constant until reflection starts appearing at the system, and at this point the current is reversed. The red curve represents the result using the driven Liouville van Neumann equation, and we can see that using this equation we can now have a clear and steady state current, and comparing the two results to the steady state Landauer current marked in an X, we can ensure our results. As I said, the main advantage when working with the state representation is that now we can use the Fermi-Dirac distribution and have a specific bias voltage and lead electronic temperature. So we can actually control the occupancy on each of the leads by controlling the bias and the temperature. Here we can see the current as a function of time again for different bias voltages, and we can see that as we increase the bias, we increase the Fermi window, and as a result we're getting a higher steady state current. Here we can see again the current as a function of time for two systems. In both systems, bias is 0. So the first system marked in red, a system where we have the same temperature on both leads, so we have the same occupancies on both leads, and the steady state current is equal to 0. Second system marked in black, a system where we have 300 degrees Kelvin on the left, 10 degrees Kelvin on the right. So we have different temperatures, therefore we have different occupancies, and the steady state current is higher than 0. So we can see that using this approach, we can now predict thermal effects in molecular junctions. Using this approach, we are also able to describe multi-lead configurations. For example, here we have a 3-lead model. So we can have different occupancies on each of the leads to have different couplings to the molecule and to measure the current at each point in the model. Also, it is important to note we are fulfilling the Chaoul's force law. Finally, we wanted to explore the influence of dimensionality and geometry on the time-dependent current. Using the molecule lead coupling scheme, we are getting from our site to state transformation. And again, our starting point is the site representation, and we are building the Hamiltonian for this atomistic picture. Here we have 3 different models. All of them are in a 2-dimensional lead model. We can see we have the same lead model, but different coupling to the molecule. So for the first example, the molecule coupled to the first row in the lead, then in the second, and finally in the third row. And after building the Hamiltonian, we can now transform to the state representation. And in the state representation, we can actually calculate the effective coupling of a specific level in the molecule to all the states in the lead. And in this example, we calculated the effective coupling of the HOMO level in the molecule to all the states in the left lead. And since the meaning of the effective coupling is the strength of the lead molecule interactions, we can see that for different geometries, we're getting different effective couplings. So finally, we plotted the current as a function of time for those 3 models, and we can see that as expected, as the effective coupling is increasing, the steady state current is higher. To conclude, a driven Liouville van Neumann equation was presented, and a site-to-state transformation has been suggested to use in electronic transport calculations. Using those two methods, we are now able to reproduce the steady-state Landauer current, to have a specific bias voltage and lead electronic temperature, and to describe multi-lead configurations, different geometries, and dimensionalities, and to explore its influence on the time-dependent current. And the take-home message is that now we can have a method that efficiently describes electron dynamics in realistic models of open quantum systems. I would like to thank Oded Hod and to the Hod group, to the Orchronic and to the Chronics group, to Avraham Nitzan from Tel Aviv University, and to Tamar Zeidman from Northwestern University, to the Nanocenter for their amazing contribution over the last 5 years. Thank you. And thank you.
Thank you, Tony. Question.
So, does your approach also include interactions, things like Coulomb blockade?
No, not yet. We are working on continuing to an extended Hicker model and to go to an orthogonal basis, and then we can start including all those interactions. This is a simple tight binding model.
When you determine the Hamiltonian, you assume the coupling between HR and HL is 0.
Yeah.
You try to calculate if there is a quantum coupling.
No, we're assuming that the leads are far enough so they won't have any interaction between them.
How far should they be?
Enough that they won't have any interactions. It's enough for several nanometers because the molecule is only.
Like a number of estimation of the digits in units? How much?
I assume that several nanometers because the molecule is in between. If I understand the question.
Any other questions? If not, let's thank Tami again.